Imagine holding a single grain of sand between your fingers. Now imagine trying to divide that grain, cutting it in half, then in half again, and again, relentlessly, until the very concept of cutting begins to lose its meaning. How far could you go? What would you find at the very end of that journey into the infinitely small? This question, deceptively simple, almost childlike in its curiosity, has driven some of the greatest minds in human history across more than 2.5 millennia of thinking, experimenting, arguing, and discovering. The answer they eventually uncovered did not merely satisfy curiosity. It reshaped civilization. It gave us nuclear energy, modern medicine, the computer you are reading these words on, and the GPS satellites silently orbiting overhead. It revealed that the universe operates by rules so strange and so counterintuitive that even the scientists who discovered them struggled to believe what the mathematics was telling them. The answer, of course, is the atom. But the atom, as it turned out, is nothing like anyone expected. It is not a hard little marble. It is not a miniature solar system. It is something far stranger, far more beautiful, and far more consequential. This is the story of how humanity came to understand the invisible architecture upon which all of reality is built. The story begins, as so many great intellectual adventures do, in ancient Greece. Around 450 BCE, on the sun-drenched Aegean coastline, a philosopher named Democritus of Abdera was wrestling with a question that had kept thinkers awake for generations. What is everything made of? Democritus was not working alone. He built upon the ideas of his mentor Leucippus, and he was entering a debate already crowded with competing theories. Some philosophers argued that all matter was made of water. Others insisted on fire or air or a combination of 4 fundamental substances. Democritus took a radically different approach. He proposed that if you divided any piece of matter small enough, you would eventually reach a particle so tiny and so fundamental that it could not be cut any further. He called this particle the atomos, Greek for uncuttable. In Democritus's philosophical vision, atoms were eternal, indestructible, and infinite in number. They moved through empty space, the void shore, and the different properties of matter arose from the different shapes and arrangements of atoms. Honey was sweet because its atoms were smooth and round. Iron was hard because its atoms were rough and interlocking. Everything that existed was simply a different configuration of these fundamental particles dancing through nothingness. It was a breathtaking leap of imagination. Without a single experiment, armed only with logic and philosophical reasoning, Democritus had arrived at a concept that would, 2,000 years later, be proven essentially correct in its most basic outlines. Yet Democritus lost the argument. The far more influential philosopher Aristotle dismissed the atomic concept entirely, preferring the 4-element model and rejecting the idea of empty void. Since Aristotle's authority dominated Western intellectual life for nearly 2 millennia, the atom was shelved, a brilliant idea filed away and largely forgotten, while chemistry and natural philosophy developed along entirely different lines. It would take until the 17th century before the stage was properly set for the atom's scientific comeback. In 1661, the Irish chemist Robert Boyle published The Skeptical Chymist, a landmark text that attacked the ancient 4-element theory and began drawing careful distinctions between chemical elements and compounds. Boyle did not revive atomic theory directly, but he built the experimental and conceptual framework, the careful measurement, the systematic chemistry that would eventually make atomic theory not merely a philosophical speculation, but a scientific necessity. The atom's scientific rehabilitation began in earnest in the English town of Manchester. in the opening years of the 19th century in the mind of a quiet, colorblind Quaker schoolteacher named John Dalton. Dalton was a meticulous experimenter. He spent years studying the properties of gases, measuring how they mixed, how they behaved under pressure, how they combined with each other in chemical reactions. And in the data, he noticed something remarkable. When elements combined to form compounds, they always did so in fixed ratios by mass. Water was always 8 parts, oxygen to 1 part, hydrogen by weight. Carbon dioxide always combined its elements in the same proportions. This was not coincidence. This was a pattern that demanded an explanation. In 1803, Dalton proposed his atomic theory, the first truly scientific version of the ancient idea. His framework was elegant and powerful. Every element, he argued, is composed of tiny, indivisible particles called atoms. All atoms of a given element are identical to each other and have the same mass. Atoms of different elements have different masses. Chemical reactions are simply the rearrangement of atoms into new combinations. No atoms are created or destroyed, merely reshuffled. This was science, not philosophy. It explained the fixed ratios Dalton had observed. It predicted how substances would combine. It was testable, falsifiable, and productive. Almost immediately, it began generating new discoveries and new questions. Other chemists rushed to measure the relative masses of different atoms. The concept of the atomic weight became central to chemistry. The intellectual momentum Dalton set in motion would, just over 6 decades later, produce one of the most famous documents in the history of science. In 1869, a Russian chemist with wild hair and a legendary personality, Dmitri Mendeleev, noticed that when elements were arranged in order of their atomic weights, striking patterns emerged. Elements with similar chemical behaviors appeared at regular intervals. Mendeleev organized these patterns into the periodic table of the elements, a chart so powerful and so predictive that when gaps appeared in its structure, Mendeleev boldly declared that undiscovered elements must exist to fill them. He even described the properties these missing elements should have. He was right. Gallium, scandium, and germanium were subsequently discovered, matching his predictions with uncanny precision. The periodic table remains, to this day, one of the most elegant and useful organizing documents in all of science, a direct consequence of taking atoms seriously. By the end of the 19th century, the atom had been promoted from philosophical speculation to scientific cornerstone. Chemists used it confidently. The periodic table organized it beautifully. There was just one remaining assumption. Atoms were still considered indivisible. Dalton's original formulation held. The atom was the bottom of the barrel. Then, in 1897, a meticulous English physicist named C.A.J. Thomson switched on a glass tube and changed everything. Thomson was experimenting with cathode rays, mysterious beams of something that shot across evacuated glass tubes when a high voltage was applied. He subjected these rays to electric and magnetic fields and measured how they bent. By carefully analyzing the deflections, he was able to calculate the ratio of the charge to the mass of the particles carrying the beam. What he found was extraordinary. The particles were far lighter than any known atom, nearly 2,000 times lighter than even the lightest element, hydrogen. And regardless of what material he used for his cathode, he always got the same particles. Thomson had discovered the electron, a tiny, negatively charged particle that lived inside atoms. The atom, it turned out, had interior structure. Democritus had been wrong about indivisibility. Dalton's model needed revision. The bottom had a basement. Thomson did his best to incorporate this discovery into a new model of the atom. Since atoms are electrically neutral overall, and electrons are negatively charged, there must be some positive charge in the atom to balance things out. Thomson imagined the atom as a sphere of diffuse positive charge, with electrons embedded within it like raisins in a pudding, or, in the phrase that has stuck to the model ever since, like plums in a plum pudding. It was a reasonable first attempt, a placeholder model that acknowledged the new reality while waiting for better data. The better data arrived with devastating speed, courtesy of one of the most remarkable experiments in scientific history. Ernest Rutherford was a New Zealander of enormous physical presence and infectious enthusiasm, often described as the greatest experimental physicist since Faraday. By 1909, working at the University of Manchester with his colleagues Hans Geiger and Ernest Marsden, Rutherford designed an experiment to test Thomson's plum pudding model. He aimed a beam of positively charged alpha particles, already known to be products of radioactive decay, at an extremely thin sheet of gold foil, and placed detectors all around to see where the particles ended up. If the plum pudding model were correct, the alpha particles should pass straight through the diffuse positive charge of the gold atoms, deflecting at most by tiny angles like cannonballs passing through fog. Most of them did exactly that, but some didn't. A small fraction of the alpha particles bounced back at large angles. A very few came almost straight back toward the source. Rutherford's famous reaction captures the enormity of the discovery perfectly. He later wrote that it was almost as incredible as if you fired 15-inch shells at tissue paper and they came back and hit you. The conclusion was inescapable. The positive charge of the atom was not spread out in a diffuse cloud. It was concentrated in a tiny, dense region at the atom's center, a nucleus so small that if the atom were the size of a football stadium, the nucleus would be a marble at the center. The rest of the atom was almost entirely empty space, with electrons orbiting somewhere in the vast emptiness surrounding this dense core. The nuclear model of the atom was born. In 1919, Rutherford pushed further, identifying the proton as a fundamental particle of the nucleus, a positively charged particle whose number determined which element an atom belonged to. Chablis Part 4. The Quantum Revolution. Rutherford's nuclear model was a triumph, but it carried a fatal flaw that classical physics could not explain. According to the well-established laws of electromagnetism, a charged particle moving in a curved path, like an electron orbiting a nucleus, must continuously radiate energy. If electrons were truly orbiting the nucleus like planets around a sun, they should spiral inward within a fraction of a second, causing all matter to collapse instantaneously. Clearly, atoms were stable. Something was profoundly wrong with the classical picture. The resolution to this crisis did not come from tinkering with existing theories. It came from an entirely new framework, one of the most radical intellectual revolutions in human history, quantum mechanics. The quantum revolution had actually begun in 1900, rooted in a problem that sounds mundane but proved transformative. The German physicist Max Planck was trying to explain the spectrum of light emitted by hot objects, a classical but stubborn puzzle. Classical theory predicted that objects should radiate infinite energy at short wavelengths, a catastrophic result physicists called the ultraviolet catastrophe. To make his equations match experimental data, Planck was forced to introduce a bizarre assumption. Energy was not emitted continuously, like water from a faucet, but in discrete packets he called quanta. The energy of each quantum was proportional to the frequency of the light, governed by a tiny constant that now bears his name, Planck's constant, Haller, Planck himself, was uncomfortable with this idea, considering it a mathematical trick rather than physical reality. But the young Albert Einstein took it seriously. In 1905, he used Planck's quanta to explain the photoelectric effect, proposing that light itself was composed of discrete particles, photons. The quantum was real. Into this strange new world stepped a young Danish physicist named Niels Bohr. In 1913, Bohr proposed a revolutionary model of the atom that married Rutherford's nuclear structure with quantum ideas. Electrons, Bohr argued, did not orbit the nucleus in just any path. They were confined to specific allowed orbits, each corresponding to a fixed energy level. An electron in one of these permitted orbits would not radiate energy and spiral inward. It was stable. An electron could only change orbits by absorbing or emitting exactly the right quantum of energy to match the difference between energy levels. The equation governing the energy of emitted photons was elegant. LEG EHFS, where Ag is Planck's constant and Phi is the frequency of the emitted light. This model had immediate, spectacular success. It explained the spectral lines of hydrogen, the precise, discrete colors of light that hydrogen emits when excited, with extraordinary accuracy. Each line corresponded to an electron jumping between specific energy levels. The match between Bohr's predictions and experimental measurements was almost perfect. It was a landmark moment. Quantum theory had made a concrete, quantitative prediction about atomic structure, and reality had confirmed it. But the Bohr model, brilliant as it was still an incomplete patchwork, quantum ideas grafted onto classical orbits. The deeper truth was stranger still. In 1924, the French physicist Louis de Broglie made a startling proposal. If light could behave as both a wave and a particle, as Einstein had shown, then perhaps matter could too. Perhaps electrons had wave-like properties. His equation was beautifully simple. Every particle has a wavelength lambda given by lambda fracas EPPP, where fracas EPPPP, PPPPPP, where pa is the particle's momentum. This wave-particle duality was not metaphor. It was measurable, testable, and real. The Austrian physicist Erwin Schrödinger took de Broglie's insight and built it into a complete mathematical theory. In 1926, he published his wave equation, one of the most celebrated equations in physics, which described electrons not as point particles following defined paths, but as wave functions spread through space. The square of the wave function at any point gave the probability of finding the electron there. Electrons did not orbit the nucleus in neat circles. They existed in diffuse, probabilistic orbitals, regions of space where they were more or less likely to be found. I bar frax partial PC partial T hat hat. Heb C parlor. This is the time-dependent Schrödinger equation, the master equation of quantum mechanics, where Sieb C Planck'schen. Ib C parlor is the wave function, Ib Barler is the reduced Planck constant, and hat hat Haller is the Hamiltonian operator representing the total energy of the system. And simultaneously, the German physicist Werner Heisenberg struck what may be the deepest blow of all to classical intuition. His uncertainty principle, formulated in 1927, stated that it was fundamentally impossible, not merely technically difficult, but impossible in principle, to simultaneously know both the exact position and the exact momentum of a particle, delta x text dot, delta x text dot, delta p jex kex bar half to 2 delta. The more precisely you pin down where an electron is, the less you can know about how fast it is moving, and vice versa. This was not a limitation of instruments. It was a feature of reality itself. The universe, at its most fundamental level, is inherently probabilistic. The electron does not have a definite position until it is measured. Until then, it exists in a superposition of possibilities. This was and remains philosophically staggering. It means the atom is not a miniature clockwork mechanism. It is a shimmering, probabilistic quantum object defined by statistics and wave functions rather than precise trajectories. Neutrons, fission, and the power within quantum mechanics had revolutionized the understanding of electrons. Meanwhile, another piece of the atomic puzzle remained stubbornly missing. Atomic masses did not match up with proton numbers alone. Hydrogen, with one proton, had a mass of roughly one atomic mass unit. Helium, with two protons, had a mass of 4. The extra mass had to come from somewhere. Physicists suspected there was another particle in the nucleus, neutral in charge, which explained why it had been so hard to detect. In 1932, James Chadwick confirmed this suspicion by carefully analyzing the results of nuclear bombardment experiments. He identified the neutron, a particle with approximately the same mass as the proton, but carrying no electrical charge. The basic three-particle picture of the atom was now complete: a nucleus of protons and neutrons, surrounded by a cloud of electrons. The number of protons determined the element. The number of neutrons could vary, producing different isotopes of the same element. This discovery had immediate, profound consequences. The existence of neutrons explained nuclear masses, but, far more dramatically, it opened the door to a new realm of nuclear physics. Unlike protons, neutrons carried no charge and were therefore not repelled by the positively charged nucleus. A neutron could be fired directly at a nucleus with no electrical barrier to overcome. In 1938, in Berlin, the German chemists Otto Hahn and Fritz Strassmann did exactly that with uranium, and obtained a result so surprising they could scarcely believe it. When uranium was bombarded with neutrons, instead of producing a slightly modified heavy element as expected, it split. Uranium atoms were breaking apart into lighter elements, barium and krypton, and releasing enormous quantities of energy in the process. Their colleague Lise Meitner, who had been forced to flee Nazi Germany but remained in close correspondence with Hahn, correctly interpreted the physics. The uranium nucleus had undergone fission, splitting into smaller fragments while converting a tiny amount of mass directly into energy, following Einstein's famous equation, while E m cap 2 libellus. The amount of energy released per fission event was small by everyday standards, but a single gram of uranium contains roughly 2.56 times 1021 atoms. If each one fissions, and if fission of each nucleus releases neighboring neutrons that trigger more fissions in a Kumchen reaction, the cumulative energy release is almost incomprehensibly large. This realization, achieved in the shadow of a gathering world war, created one of history's most charged moments of scientific drama. The Italian physicist Enrico Fermi, who had already done pioneering work on neutron-induced reactions, led a team at the University of Chicago that in December 1942 achieved the first controlled nuclear chain reaction below the stands of an old football stadium in a structure they called Chicago Pile 1, a careful arrangement of uranium fuel and graphite moderator the size of a small building. Fermi's team slowly withdrew their control rods and watched the neutron counters rise. Humanity had, for the first time, deliberately unlocked the energy stored inside atomic nuclei. The military implications were devastatingly clear. The Manhattan Project, driven by fear that Nazi Germany was pursuing the same capability, mobilized the most extraordinary concentration of scientific talent in history. Under the scientific direction of J. Robert Oppenheimer at a secret laboratory in Los Alamos, New Mexico, teams worked to engineer the first atomic bomb. On July the 16th, 1945, at the Trinity test site in the New Mexican desert, the device was detonated. The explosion released energy equivalent to approximately 21 kilotons of conventional explosive. Oppenheimer, watching the fireball rise, quoted from Hindu scripture, "Now I am become death, the destroyer of worlds." 3 weeks later, atomic bombs were dropped on Hiroshima and Nagasaki. The human consequences were catastrophic. The world had fundamentally changed. For a time, it seemed as though this trio, three fundamental particles organized by quantum mechanics, might truly be the final answer. But science, by its nature, keeps digging. In 1964, the American physicist Murray Gell-Mann examined the growing menagerie of particles being produced in high-energy accelerator experiments and proposed a startling unifying theory. Protons and neutrons were not fundamental at all. They were themselves composed of still smaller particles, which Gell-Mann whimsically named quarks, a word plucked from James Joyce's Finnegan's Wake. In Gell-Mann's model, a proton consists of two up quarks and one down quark, while a neutron consists of one up quark and two down quarks. Quarks carry fractional electric charges, plus frac 233 Ohlers, or R, fracs 133 Ohlers of the fundamental charge unit, and they are bound together by an entirely new force, the strong nuclear force, carried by particles called gluons. One of the stranger properties of the strong force is that quarks cannot be isolated. Try to pull a quark out of a proton, and the energy you put in is sufficient to create a new quark-antiquark pair. The proton heals itself. Quarks are permanently confined inside composite particles called hadrons. The quark model was progressively validated over the following decades. 6 types or flavors of quarks were predicted and eventually discovered. The last of these, the top quark, extraordinarily heavy and requiring enormous energies to produce, was finally observed at the Traco Accelerator near Chicago in 1995, completing the quark family and substantially confirming the theoretical framework. The broader framework within which quarks, electrons, and all other fundamental particles fit together is called the SES Standard Model of particle physics, arguably the most successful scientific theory ever devised. It describes 3 of the 4 fundamental forces: electromagnetic, weak nuclear, and strong nuclear, and accounts for the behavior of all known fundamental particles with breathtaking accuracy. Some of its predictions have been verified to better than 1 part in a trillion. The Standard Model received spectacular additional confirmation in 2012 when physicists at CERN's Large Hadron Collider, the most complex machine ever built by human beings, a circular particle accelerator 27 kilometers in circumference, buried beneath the French-Swiss border, announced the discovery of the Higgs boson. The Higgs particle, predicted in 1964 but never previously observed, is associated with the mechanism by which fundamental particles acquire mass. It was the final missing piece of the Standard Model, and its discovery sent scientific celebrations rippling around the globe. At each layer of depth, atom, nucleus, proton, quark, the universe revealed new complexity, new beauty, and new laws. Byte, Part 7, The Atom at Work in the Modern World. The journey from Democritus's philosophical speculation to Gell-Mann's quarks and the Higgs boson is one of humanity's greatest intellectual adventures. But the atom is not merely a chapter in the history of ideas. Its understanding has been transformed into technologies that define modern life in the most practical and intimate ways. Nuclear power stands as the most dramatic, large-scale application of atomic knowledge, controlled fission reactions. The same process Fermi first demonstrated in Chicago in 1942 today power approximately 440 nuclear reactors around the world, generating roughly 10% of global electricity. In countries like France, nuclear power provides over 70% of national electricity generation. A single kilogram of uranium fuel contains energy equivalent to approximately 3,000 tons of coal, with no carbon dioxide emissions during operation. In an era of mounting urgency over climate change, nuclear fission's capacity to provide large-scale, low-carbon baseload power has returned it to serious policy attention. And fission may only be the beginning. The fusion reaction, which powers the sun itself, fusing hydrogen nuclei into helium and releasing vastly more energy per unit mass than fission, has long been described as the clean energy holy grail. The International ITER project in southern France, supported by 35 nations, including the US, China, and the European Union, is constructing the world's largest fusion experiment, a device designed to demonstrate that more energy can be extracted from a fusion plasma than is put in to maintain it. If successful, fusion could ultimately provide virtually limitless clean energy using hydrogen isotopes extractable from seawater. In medicine, the atom is equally transformative. A radiation therapy uses carefully directed beams of high-energy particles to destroy cancer cells with remarkable precision, saving millions of lives annually. PET scans, C, positron emission, tomography, introduce tiny quantities of radioactive tracer molecules into the body. As these decay, they emit positrons that annihilate with electrons and produce gamma rays whose origin can be precisely located, generating detailed images of metabolic processes in living tissue. Radioactive iodine treats thyroid cancer. Technetium-99m illuminates the cardiovascular system for diagnostic imaging. The atom has become one of medicine's most powerful allies. Perhaps the most pervasive application of atomic theory is one rarely recognized as such. A quantum mechanics, BUS, the theory born from the crisis of understanding electrons in atoms, is the foundational science of the semiconductor industry. The transistor, invented in 1947 and now fabricated at scales below 10 nanometers, operates on quantum mechanical principles that classical physics simply cannot describe or predict. Modern integrated circuits pack billions of transistors onto a chip the size of a fingernail. Every smartphone, every laptop, every server farm, every internet router depends on quantum mechanics for its operation. The digital age is a quantum age. Atomic clocks exploit the quantum mechanical property that atoms of a given element absorb and emit radiation at extraordinarily precise, stable frequencies. A cesium atomic clock keeps time accurate to roughly 1 second in 300 million years. This precision is not academic. It is the operational backbone of the SEEK Global Positioning System, GPS satellites. GPS satellites carry atomic clocks, and the system's ability to determine your location to within a few meters depends entirely on measuring time delays in signals accurate to billionths of a second. Every time you use navigation on your phone, the atom is doing work on your behalf. Nanotechnology and materials science now manipulate matter at the level of individual atoms and molecules, engineering materials with properties tailored at the quantum scale. Carbon nanotubes are stronger than steel at a fraction of the weight. Graphene, a single layer of carbon atoms arranged in a hexagonal lattice, has extraordinary electrical and mechanical properties. Quantum dots allow scientists to tune the color of emitted light by simply changing the size of semiconductor nanocrystals. The ability to understand and control matter at the atomic scale is opening a new era of materials design. We have traveled an extraordinary distance from the sun-baked colonnades of ancient Abdera, where Democritus first imagined his atomos. What he envisioned as a simple, indivisible, solid particle has revealed itself to be a dazzling nested structure of increasingly strange and counterintuitive layers, quantum electrons in probabilistic clouds, a dense nucleus of protons and neutrons, and those protons and neutrons themselves composed of quarks bound by the most powerful force in nature. The atom is not the bottom. Every time physicists thought they had found the final layer, reality revealed another staircase descending further. Whether quarks and electrons are themselves composed of something still smaller, perhaps the tiny vibrating strings of string theory, or some other structure not yet imagined, remains one of the great open questions in physics. The Standard Model, for all its triumphs, leaves gravity unaccounted for, says nothing satisfying about dark matter or dark energy, and feels to many physicists like an incomplete chapter in an ongoing story. Yet what has already been discovered is staggering. The atom is 99.9999999999999. The proton is roughly 100,000 times smaller than the atom. The quark is at least 10,000 times smaller than the proton. The nucleus, if it were the size of a cricket ball, would make the atom as large as a major international stadium. And yet, in that vast emptiness, quantum mechanics weaves its strange probabilistic tapestry, and the result is you, reading these words, composed of atoms forged in the nuclear furnaces of dying stars, temporarily organized into consciousness, contemplating the nature of your own construction. The atom is not merely a scientific concept. It is a mirror. In understanding it, we understand where we came from, the star stuff of our constituent elements, the quantum laws that hold our molecules together, the nuclear processes that sustain the sun that sustains all life on our planet. In learning to harness it, we have demonstrated both our greatest ingenuity and our gravest capacity for destruction. In continuing to probe its deepest layers, we pursue the oldest and most human of ambitions, to understand the world as it truly is, all the way down to its most fundamental, irreducible nature. The atom is everything, and understanding it changes everything. The atom, smaller than imagination, larger than consequence,